My name is Dr. Adum Babu, Associate Professor in EC Department. In this lecture, I am going to discuss on the topics Total Probability Theorem, Bayes Theorem and different types of random variables. First, we will discuss about the Total Probability Theorem. Total Probability Theorem means in a sample space S, I am defining the total probability of an event A with respect to conditional probabilities of K mutually exclusive events which was defined in the sample space S. Suppose this is the sample space S of any experiment. In this sample space, I am having the K mutually exclusive events B1, B2, B3 and so on Bk. I am defining a one total probability of event A with respect to conditional probabilities of K mutually exclusive events. Here, the union of all these mutually exclusive events, are total sample space S. This is union of K is equal to 1 to n, Bk is equal to total sample space S. Then the total probability of A in this sample space S of any experiment P of A is equal to summation of K is equal to 1 to n P of A by Bk into P of Bk. This is the total probability of event A in a sample space S which are having K mutually exclusive events. This is the statement of the total probability theorem. Now we will discuss the proof of the total probability theorem. In this sample space, I am defining the event A intersection A is equal to A, and S is the union of K mutually exclusive events. S is defined as union of K is equal to 1 to n peak. So this can be A intersection summation of K is equal to 1 to n Bk is equal to, again I am writing as union of K is equal to 1 to n A intersection Bk. Apply probability on both sides, then P of A is equal to P of A intersection S, but A intersection S is equal to P of union of K is equal to 1 to n A intersection Bk. Next, I am expanding these events from K to K is equal to 1 to n, that is P of A intersection B1 union P of A intersection B2 union P of A intersection B3 union and so on A intersection Bn. Here B1, B2, B3 all are mutually exclusive events. If any two events are mutually exclusive events, then P of A union B is equal to P of A plus P of B. If here A and B are mutually exclusive events, then union of those mutually exclusive events is sum of their individual probabilities. This is the axiom 3. So here B1, B2, B3, Bk are mutually exclusive. Then union is converted into summation. Summation of K is equal to 1 to n P of A intersection Bk. Then P of A is equal to, I am defining this one. Next, P of A intersection B1 can be written as P of B1 into P of A by B1. This is from multiplication theorem. This can be written as summation of K is equal to 1 to n P of A by Bk into P of Bk. So this is the total probability of event A. So P of A is equal to summation of K is equal to 1 to n P of A by Bk into P of Bk. Now I will discuss some example based on the total probability theorem. In this problem, I am having the IC manufacturing plant. In this, three sources A, B, C manufactures the ICs, and each IC is manufactured by different sources. The defective IC probabilities are also given 0.001, 0.002, 0.003. So what is the probability of any given radio will contain a defective IC? So I have to find out the total probability of defective IC that is manufactured by any one of the sources, that is A, B, C. So first of all, I am having the three sources A, B, C. So probability of IC from source A is equal to 1 by 3. Probability of IC coming from the source B is also 1 by 3. Probability of IC coming from source C is also 1 by 3. Three are having the equal probabilities. A, B, C sources are having the equal probabilities. Next, probability that the defective IC comes from A only. First, I am selecting the source A. Next, IC is manufactured that is defective, that probability is 0.01. Similarly, probability that the defective IC comes from source B is also 0.003. Probability that the defective IC comes from source C is also P of D by C is also 0.002. Here I have to find out the defective IC that comes from any one of the three sources. So probability of defective IC is equal to, from the total probability theorem, P of A into P of D by A, P of B into P of D by B, P of C into P of D by C. Here I am having the three sources. I am taking the summation of three sources. First source is from source A, second source is from source B, third IC is from source C. So P of A is 1 by 3, P of B is 1 by 3, P of C is also 1 by 3, P of D by A, P of D by B, P of D. After substituting all those values, then I will find out the total probability of defective IC from any one of the sources A comma B comma. So this is by using the total probability I solve this problem. Next, coming to the Bayes theorem. In the Bayes theorem, here B1 comma B2 comma B3 are mutually exclusive and exhaustive events in any sample space A. Then probability of event A defined in any S is P of Bk by A is equal to P of Bk into P of A by Bk, summation of P of Bk into P of A by Bk. This is the Bayes theorem statement. And the proof is, generally P of B by A is equal to, that is the conditional probability, P of B by A is equal to P of B intersection A by P of B. P of B intersection A can be written, this is from, by using multiplication theorem, I am writing as P of B intersection A can be written as P of B into P of A by B. This P of A already I derived from the total probability theorem. So P of A is equal to summation of K is equal to N, then P of A by Bk into P of that same value I am using in the Bayes theorem. So P of A is equal to summation of K is equal to 1 to N P of Bk into P of A by Bk. Okay, this is the proof of the Bayes theorem. Now I'll discuss the one example on the Bayes theorem. Here in this example, 49% of population are female. Of the female patients, 8% are high risk for the heart attack, while 12% of the male patients are high risk for heart attack. A single person is selected at the random and found to be high risk. What is the probability that it is male? So here, out of the population, 49% are female, remaining percent are male, and 8% of among those female, 8% are risk for heart attack, and 12% of male are risk for heart attack. So here I am defining the events. H is the high risk and F is the female and M is the male. You know that probability of female is equal to, out of total population is 49%, so that is 0.49. Remaining percent is equal to 51. From 100, 49% are female, remaining 51% are male, so probability of male percentage equal to 0.51. So the risk of heart attack of female, after selecting the female, risk of heart attack I am assuming as H is the heart attack. So P of H by F is equal to 8%, that is 0.008. Next, P of H by M is equal to 0.12, that is the 12% of male are heart attack. Now I have to find out the what is the probability that is the male who is affecting the heart attack. This is from Bayes theorem. P of M by H is equal to P of M into P of H by M. Next, this is the total probability of heart attack. P of H, P of M into P of H by M, P of F into P of H by F. P of M values and P of H by M values, P of F value. After substituting this value, I will find out the total probability that the male is affected by the heart attack. This is solved by using the Bayes theorem. Next, one more example is, here bag 1 contains 4 white balls and 6 black balls, and another bag contains 4 white balls and 3 black balls. One ball is drawn at random from any one of the bags and it is found to be black. Find the probability that it comes from bag 1 only. Here first I am defining the events. E1 is the event of choosing bag 1, E2 is the event of choosing bag 2, and AB the event of drawing black ball. I am having the two bags. Probability of selecting any one of the bag is equal to 1 by 2 only. Both are having the equal probability. Next, after selecting the ball, I have to draw the black ball. So after selecting the first bag, drawing the black ball is equal to, here I am having the 6 black balls and total balls is equal to 6 plus 4 10 balls. So that is equal to 6C1 by 10C1. Out of 10 balls I am drawing the one ball. That ball is nothing but black ball. So 6C1 by 10C1, that is 6 by 10, that is equal to 3 by 5. Next I am selecting the bag 2. In the bag 2 I am drawing the black ball. In the bag 2 I am having the 3 black balls and total balls are 7. So 7 balls. Out of 7 balls I am taking the one ball and black balls are 3, that is equal to 3C1 by 7C1, that is 3 by 7. Next I am finding the total probability of black ball. So P of E1 into P of A by E1 plus P of E2 into P of A by E2. 1 by 2 into 3 by 5 plus 1 by 2 into 3 by 37. But I have to find out the probability that it comes from bag 1 only. Here I am applying the Bayes theorem. So E1 is the bag 1. So coming of black ball that comes from bag 1 only. P of E1 by A is equal to P of E1 by E1 into P of A by E1 divided by P of A. This is the total probability. Already we calculated the total probability of black ball. So P of E1 by A is equal to P of E1 into P of A by E1 divided by P of A. So 1 by 2 into 3 by 5 divided by 36 by 70, that is equal to 7. This is the probability of selecting black ball that comes from bag 1 only. That is the difference between Bayes theorem and total probability. Means we are finding the total probability of black ball that comes from any one of the bags, that comes from either bag 1 or bag 2. Here Bayes theorem finding the probability of selecting black ball that comes from bag 1 only. Okay. Next one is random variable. Random variable is nothing but we are assigning the some real value to each and every outcome of any experiment. In experiment we are having the sample space and we are assigning the some real value to each and every outcome of that experiment. Here I am having the one experiment. If 2 coins are tossed, I am having the 4 possible outcomes, that is the head tail and tail head, tail tail and head head. These are the 4 sample points of this experiment. Now I am defining the one random variable x that is equal to number of heads. In the first sample point I am having the one head, that is 1. Next sample point 1 head. Third sample point I don't have any heads, that is equal to 0. And fourth sample point I am having the 2 heads. So the random variable x values for this experiment is equal to 1, 1, 0, 2. I am defining as random variable as number of heads. So I am assigning the some real value to each and every outcome of any experiment, that is said to be random variable. Here one more example is exam score of a randomly selected student. So I am having a number of students. In every student is having some exam score, that is we are assigning some value. Next, number of people in a room at a randomly selected at a time of day. Number of people as also we are assigning some number. Number of upper face of randomly tossed die. If die is rolled, my sample space is 1, 2, 3, 4, 5, 6. I am assigning some value. That is the x is equal to number of the any upper face. After rolling a die, what is the number on the upper face? This is the random variable definition. Next, what are the conditions for a function to be a random variable? So every random variable shall be an event for any real number of x. This is the first condition. Next, the probability of any event p of x less than or this event p of x less than or equal to x is equals to sum of probability of all elementary events corresponding to x less than or. That means suppose x less than or equal to 2. This is my event. Then probability of x less than or equal to 2 means p of x is equal to 0 plus p of x is equal to 1 plus p of x is equal to 2. That means sum of probability of all these three elementary events corresponding to this event. Next condition is the probability at x is equal to minus infinity is equal to 0, the x is equal to plus infinity. The value lies between these two values, but at x is equal to minus infinity and x is equal to plus infinity, the values are 0. These are the three different conditions for a function to be a random variable. Next, I am having the types of random variable. We are having two types of random variable. That is, one is the discrete random variable and another one is the continuous random. Discrete random variable is nothing but it is having countable number of outcomes. It is having only finite number. Suppose a die is rolled. The values are 1, 2, 3, 4, 5, 6. This is the discrete random variable. It is having some finite outcomes, finite countable outcomes. Here example is dead or alive and treatment and dice counts. Next, coming to the continuous random variable, it has an infinite values of the infinite possible values in a certain limits. That means if I am having the limit 1 to 10, it will take all continuous possible values between a range 1 to 10. Here example is called blood pressure, that is the infinite. Weight is also infinite. Then speed of a car and real numbers from 1 to 6. So it will take all possible values in a certain limits or continuous values in a certain limits, that is said to be continuous random variable. These are the topics covered in this lecture, that is the total probability theorem, Bayes theorem and different types of random variables. Thank you.